Okay. Good evening, Rakshan.
Good evening, ma'am.
So we have been discussing organic chemistry, right?
Yes.
So you have organic chemistry in 10th standard, right, Kana?
No,
That
ma'am.
fourth chapter, carbon and its
Yes.
compounds. That is basically organic chemistry. You have four chapters from chemistry, right? Chemical reactions and equations. Second is acid,
Acid,
base,
base, and
and
salt,
salt.
metals and
Metals,
non-metals.
non-metals. Fourth one is carbon and its compounds, right? So basically, that chapter is organic chemistry. Okay. In 11th standard, we have four chapters from organic chemistry, and in 12th standard, we have around six chapters from organic chemistry. But in 10th standard, we have only one chapter, basically that have all the raw fundamentals of organic chemistry, Kana, where you will be studying your carbon, its valency, different types of functional groups, and have to name the organic compound and all. Right? Do you remember? Do you remember, Rakshan? What are all the functional groups you have studied in that particular chapter? Usually they'll give
What, ma'am?
what are all the functional groups you have studied in that particular chapter. In the chapter called carbon and its compounds, they have discussed four functional groups, right? What are all the functional groups?
Alcohol,
Very
aldehyde,
good.
ketone,
Mm.
carboxylic acid.
Mm.
That's all.
Halo, fluorine, chlorine,
Uh,
bromine, and all, right?
Iodine.
Yes, exactly. So also they have discussed how to name that organic compound, right? Can I'll give you a compound. Can you please name it? I'm going to share my screen. Is it visible, Rakshan?
Yes, ma'am.
Okay. Kana, what functional group is this?
Alcohol.
Um, alcohol இல்லைங்க சார் இதுல வெறும் OH மட்டும் இருந்தா தான்
OH,
alcohol, but
okay,
it
okay.
is different.
CH3 where it?
CH3COOH. This can also be written as CH3COOH. What functional group is this, Rakshan?
Ethanoic acid.
Compound name is ethanoic acid. And what functional group is that? Acid. It is basically carboxylic acid. Right? So we have two carbons. So it is eth, and both the carbons are connected through single bond. So it is an, and the suffix is ioic acid. So whenever you are naming the compound, the first part is your root name, which represents number of carbon atoms. Basically, the technical word is alk. Alk represents number of carbon atoms. Next term represents number of chemical bonds between carbon atoms. If we have only single bond, then that is ANE. If we have double bond, then it is ENE. If we have triple bond, then that is YNE. Right, Kana? And if we have any functional groups, then we'll be writing the suffix of that functional group. If it is alcohol, we'll be writing it as OL. If we have aldehyde, then the suffix is AL, right? If we have ketone, the suffix is ON. And if it is carboxylic acid, the suffix is oic acid. Okay. I'm going to write another compound. Rakshan, please, can you please tell me the functional group in this compound?
Propanone, ma'am.
The compound is propanone, and what functional group is that?
Ketone.
Very good, ketone. So we have three carbons, and all the three carbons are connected through single bond. So if it is three carbon, the alk is prop, and all the three carbons are connected through single bond. So it is ANE. But we're going to add a suffix of a functional group. So I'm going to cancel that E. Instead, I'm going to add the suffix, which is on. That's it. So propanone. Very good, Kana. Could you please name this compound? It is a very famous one.
Benzene?
Yes, sir. It is benzene. Okay. What is the functional group here? Good evening, Bhumika.
Good evening.
Good evening, Kanna. Good evening, Kanna.
Aldehyde.
Very good. It is aldehyde. Could you please name this compound?
Ethanol.
Very good, Kanna. Ethanol. Right. So we'll get into the class. So last class we have been discussing reaction mechanism. Did you attend the last class, Rakshan? Did you attend our last class?
No, ma'am.
No. Okay. Fine. So what shall we do, Rakshan? Shall we discuss few questions from 10th standard, or we'll continue the topic what we are discussing, what we have been discussing in our last class? What shall we do?
Continue the topic we are discussing in last class, ma'am.
Okay, Kanna, fine. So, we have been discussing the topic called general organic chemistry, that is from 11th standard. In general organic chemistry, the topics we already discussed was carbon and its valency, what is hydrocarbon, different types of hydrocarbons, and how to name a hydrocarbon. And we have discussed the hybridization of carbon in any organic compound. We discussed functional groups and different types of functional groups, after which we discussed what is primary compound, secondary compound, tertiary compound, and all that. After which we discussed what is organic reaction, the terms we are using in organic reactions like substrate, reagent, different types of reagents, and classification of organic compound, under which we have discussed open chain, closed chain. Under open chain, we have discussed saturated, unsaturated compound. And in closed chain, we have discussed the very important topic, which is aromaticity, how to find whether the compound is aromatic or not. If the compound is not an aromatic compound, then it can be either non-aromatic or anti-aromatic. We have discussed the conditions for the compound to be aromatic, right? So the most important conditions are the compound should be cyclic, compound should be a planar one, and it should have double conjugated double bonds, and definitely it should obey Huckel's rule, which is 4n plus 2 pi electrons, right? If the compound is anti-aromatic, then again the compound should be cyclic, planar, double bonds has to be conjugated, and instead of Huckel's rule, anti-aromatic compound will have just 4n electrons. Instead of 4n plus 2 pi electrons, anti-aromatic compounds will have just 4n pi electrons. So we'll be having pi electrons, like we'll be having multiples of 4 pi electrons, right? Usually anti-aromatic compounds are highly unstable and aromatic compounds are most stable one, and we have seen so many examples under aromaticity. After which we discussed different types of organic reactions, under which we discussed addition, elimination, substitution reaction, and all that. And after which we discussed different types of reaction mechanism, under which we discussed few types of intermediates like carbocation, carbanion, and free radical, and the scenarios where we'll be getting this intermediates. And finally, we started with electronic effects. We have four electronic effects, right? One is inductive, second one is hyperconjugation, third one is mesomeric or resonance effect, and fourth one is electromeric effect. So last class we discussed inductive and hyperconjugation, and in fact we saw one problem based on that inductive and hyperconjugation, right? So understanding the stability of intermediate is very, very important. And last class I've given you the stability order of carbocation, free radical, and carbanion. As far as carbocation is concerned, tertiary carbocation is more stable than secondary. Secondary carbocation is more stable than primary. Primary carbocation is more stable than methyl carbocation. And we have seen the reason behind this also, right? As far as free radical also, tertiary free radical is more stable than secondary free radical. Secondary is more stable than primary. Primary is more stable than methyl free radical. As far as carbanion is concerned, it is completely opposite. As far as carbanions are concerned, methyl carbanions are more stable than primary, then secondary. Least is tertiary carbanion, right, Kana? So this is the order based on inductive effect. But when we have two tertiary compounds, two tertiary carbocations or two tertiary free radicals, at that time we have to check for number of alpha hydrogens. If the number of alpha hydrogens are more, stability is more, right? So that's it. So I'll give you one problem. Based on this, we'll arrange the stability of carbocation. I'm going to give you few carbocations here. I want you guys to arrange these carbocations based on the stability. This is compound A. This is B. This is C. This is D. And finally E. Can you please arrange these carbocations based on their stability? First, you have to categorize whether they are primary, secondary, tertiary, or methyl. So what kind of carbocation is this one? Positively charged carbon is attached with 3 R groups. So it is tertiary. Positively charged carbon is again attached with 3 R groups. Again, this is tertiary. Here, positively charged carbon is attached with only 1 R group. So it is primary. Here, positively charged carbon is attached with 2 R groups. Very good, Kana. It is secondary. And here we have no R group. So this is methyl carbocation. As far as carbocations are concerned, we know tertiary is most stable one, then secondary, then primary, least is methyl. So we know that tertiary carbocations are more stable. But according to this question, we have two tertiary carbocations. So whenever we have two tertiary carbocations, how we have to decide their stability? We have to count the number of alpha hydrogens. So how to do that? The carbons which are directly attached with positively charged carbons are alpha carbons. The carbon which are directly attached to alpha carbon is beta. So we have three beta carbons, and the hydrogens which are attached to alpha carbons are alpha hydrogens. Could you please tell me how many alpha hydrogens are there? How many alpha hydrogens are there?
6.
Here we have 3 alpha hydrogens. Here also we have 3 alpha hydrogens. And here we have 2 alpha hydrogens. So how many alpha hydrogens we have?
8.
Very good. Here we have 8 alpha hydrogens. And second one?
9, ma'am.
Very good, Kana. So we have 9 alpha hydrogen.
3, ma'am.
Here we no need to find number of alpha hydrogen. So because it is already primary, no. So primary is least stable. So whenever we cannot decide using inductive effect, then we have to go for hyperconjugation. Okay. So we know the general order, like tertiary is more stable, but here we have 2 tertiary systems. So that is why we gone for hyperconjugation, where we are counting this number of alpha hydrogen. So among A and B, which is most stable? The intermediate or the carbocation with more number of alpha hydrogen. So
B, ma'am.
most stable is B. Next is A. And see, both the stuffs are tertiary. Next,
D, ma'am.
D. Very good. Next,
C, ma'am.
next is
Mm.
E. Very good, Kanna. So this is tertiary, this is secondary, this is primary, and this is methyl. As far as tertiaries are concerned, this got 9 alpha hydrogen, which is most stable, and this got just 8 alpha hydrogen. That's it. Now I'm going to give you different set of carbocations. Listen here. What kind of carbocation is this? Is it primary, secondary, or tertiary?
Tertiary, ma'am.
Yes. So the first carbocation I've written is tertiary. Could you please tell me what kind of carbocation is this? Positively charged carbon is attached with only one R group. So it is, if it is connected with only one R group, then it is, yes, it is primary. Very good, Kanha. It is primary. Now we have to find the stability. Generally, what we know is tertiary carbocations are more stable. That is what the general order, right? Here, listen here, very important point. Listen here. As far as these two carbocations are concerned, B is most stable than A, because though the intermediate B is a primary carbocation, here this R group is a benzene one. So when the R group is benzene, it is most stable than the tertiary carbocation. As far as carbocation B is concerned, it is primary, because this got only one R group, but that R group is a benzene. If R group is benzene, that benzene ring will stabilize this carbocation more than the tertiary carbocation. Okay, I want to explain how it is stabilizing. Now listen, as far as tertiary carbocation is concerned, what these methyl groups are doing, positively charged carbons are considered to be electron deficient. Since this carbon is electron deficient, it is unstable. What these 3R group will be doing, this methyl group is considered to be plus I group. So plus I groups are nothing but electron donating group. So these 3 electron donating groups will push electron towards the positively charged carbon, right? So because of these 3 plus I groups, carbocation is getting the moral support, because these 3 R groups are pushing the electrons towards carbocation. So because of that, this positively charged carbon is getting the moral support from all the three R groups. But here we have only one R group, but this R group is far better than this just methyl groups. I'll justify the uh, I'll justify the stability. Listen here. Kana, listen, Kana. This is very important, and you guys have to know how to write these structures. Listen carefully. This is benzene, and this benzene ring is attached with this carbocation. We know positively charged carbon is electron deficient carbon. That carbon doesn't have electron. So what this benzene ring will do is, this benzene got 3 pi bonds, right? One of the pi bond will get transferred between these two carbon atoms. This is one carbon atom and this is one carbon atom. So this bond will get transferred between these two carbon atoms. So what will be the next structure? I'll be having same 6-membered ring. I have one pi bond here and one pi bond here. Now this bond was transferred. Already I have one chemical bond. Now I got one new chemical bond between these two carbon atoms and carbon with 2 hydrogens. Now we will not have this positive charge because the valency of this carbon is satisfied. Now the problem is for this carbon because this carbon donated its chemical bond. So this carbon is in need of electron. So this carbon is electron deficient. Now positive charge will be on this carbon atom. Okay. What will be the next step? Since this carbon is electron deficient, this bond will get transferred between these two carbon atoms. Okay, so I'm going to write the next structure. Same 6-membered ring. I have one double bond here. Now I got new double bond between these two carbon atoms, and this double bond was undisturbed. So now the problem is for this carbon because this carbon donated its bond. So this carbon will have a positive charge. Right, Kana? Now what will happen? Since this carbon is electron deficient, the bond will get transferred between these two carbon atoms. Now the next structure will be, again we will have 6-membered ring. I have one double bond here. Now I got new double bond here, and this carbon got one positive charge and this double bond is undisturbed. Finally, this double bond will get transferred between these two carbon atoms and we'll end up with the first structure itself. So this is called resonance. These structures are called resonating structures. See, in resonating structures, we'll be changing the position of the bond or position of the electron to write the different structures. And this is called resonance. Whenever we are writing the resonating structures, the system is getting stabilized. If the resonating structures are more, then structure will be, the stability will be more. So number of resonating structures are directly proportional to the stability. See, here as far as this carbocation, the carbocation which is present in B is called as benzyl carbocation. Because one of the R group is benzene, so this is called benzyl carbocation. So benzyl carbocations are more stable than your tertiary carbocation. The reason is, as far as benzyl carbocation is concerned, we have 4 resonating structures, and in 4 resonating structures, the positive charge was distributed, or it is with the other carbon atoms which is present in the benzene. And in most of the resonating structures, see, this carbon doesn't have its positive charge, right? So as far as tertiary carbocation is concerned, tertiary carbocation is just getting the moral support from all the 3 R groups. But as far as benzyl carbocation is concerned, this benzene is taking up the positive charge for some time. So this carbon will be more happier than the tertiary one, right? So benzyl carbocations are more stable than your normal tertiary carbocations because this benzene ring is taking up the positive charge from that carbon and making the carbon really a stable one. Okay. If suppose I'm going to write another structure, positively charged carbon. Here I have two hydrogens, right? I'm going to replace one more hydrogen with this benzene. So I have two benzene rings. So positive charge will be taken away by these benzene rings for some time, and positive charge will be taken away by these benzene rings for some time. So this carbocation will be even more stabilized. So this is secondary carbocation, but this is secondary benzyl carbocation. So if number of benzene rings increases, stability also increases. Okay. So the normal order is tertiary is more stable, but benzyl is even more stable than your just tertiary carbocation. Okay. I'm going to introduce another one type of carbocation. Guys, listen. This is carbocation, and this carbocation is attached with this carbon. Could you please could you please tell me the hybridization of this carbon, Kana? Hybridization of this carbon. Have to find the hybridization around carbon atom. If we have 4 single bonds, then that is sp3. If we have one double bond, then that is sp2. If we have one triple bond and one single bond, or if we have two double bond, then that is considered to be sp.
SP.
So if we have two double bonds, then that is sp. If we have triple bond and single bond, sp. But here we have only one double bond. So
SP2, ma'am.
very good. It is sp2 hybridized carbon. If a carbocation is attached with sp2 hybridized carbon, this carbocation is called allyl carbocation. Let us see how this allyl carbocation is getting stabilized. Here I have this pi bond, right? This pi bond, here I have one double bond. In double bond, one bond is sigma, another bond is pi, and we know pi bond is relatively a weaker one. So this bond is getting transferred between these two carbon atoms. So what will happen? CH2. Now we have single bond CH, double bond CH2. Now this carbon will not have its positive charge. Instead, this carbon will have a positive charge. Then the next step is now this bond will again transfer between these two carbon atoms, and we'll end up with the first structure itself. See, these two structures also called as resonating structures. As far as inductive effect is concerned, carbocations are getting just the moral support from R groups. But as far as allyl carbocation and benzyl carbocations are concerned, because of the resonance, carbocations are even more stabilized. So if you compare the stability of carbocations, this will be the final order. Listen here. If you compare the stability, benzyl carbocation is more stable than allyl because both the carbocations are stabilized by resonance. But as far as allyl carbocation is concerned, we have only two resonating structures. But in benzyl carbocation, we have 4 resonating structures. As the number of resonating structures increases, stability also increases. Okay, so benzyl is more stable than allyl. Then allyl is more stable than your tertiary. Tertiary is more stable than your secondary. Secondary is more stable than primary. Primary is more stable than your methyl carbocation. That's it. As far as free radical is concerned, the same order. Benzyl, allyl, tertiary, secondary, and primary. As far as carbanion is concerned, There also, benzyl carbanion is more stable than allyl. Allyl is more stable than your methyl carbanion. Methyl carbanion is more stable than your primary. Primary is more stable than your secondary. Secondary is more stable than your tertiary carbanion. Okay. Is that clear? So this order is very, very important, Kana. You may get questions directly from this stability of intermediates, or in 12th standard we may use this concept to understand the reaction mechanism also. So understanding the stability is very, very important. Okay, any doubt?
No.
Any doubt, Kana? Okay, fine, I'll give you a question and I want you guys to tell me the answer. Okay, I'll share you the question. Here is the question. Homolytic fission of the following alkanes forms free radicals. Of course, upon homolytic cleavage, we'll end up with free radicals, right? So they're asking us to arrange the radicals based on its stability. Please check on each option. We have different types of free radicals. Please mark them as primary, secondary, or tertiary. We have to understand that. Later, you have to arrange the arrange the free radicals based on their stability. Can you do it? Okay, I'll work out this first option. Listen here. What is the stability order of free radical? Benzyl free radical is more stable than allyl. Allyl is more stable than? What is the stability order, Kana?
Tertiary.
Very good. Tertiary, secondary, primary, and methyl. So I'm going to work on this first option. CH3 twice. It is connected with carbon with one electron. Bond CH2, CH3. Say I'm going to write this carbon with odd electron. Okay. Carbon with one electron. Right side I have CH2, CH3. On the left we have CH3 twice, which means we have two CH3 groups, right? How we have to write? See, I have one bond with one CH3 and another bond with one CH3. This is what the actual structure is. But in the option, they have given you the condensed form. Whenever the compound is given in the condensed form, we should be in a position to write in a normal way. Okay, fine. Could you please tell me what kind of free radical is this? Is it primary, secondary, or tertiary?
Tertiary.
Very good, Mushkin. It is tertiary. Now we'll work on the second one. Again, this is the carbon with only one electron. Left side, I have one methyl group. Right side, I have one more methyl group. And this odd electron is connected with one hydrogen also. Could you please tell me what kind of free radical is this?
Okay.
It is secondary because the carbon with one electron is connected with two R groups. It is secondary. Of course, we know this option is a wrong one because here the tertiary seems to be the least stable, but which is not true, right? Anyways, we'll understand how to write the structure. See, this is concern. This is the carbon with only one electron. It is connected with two hydrogen atoms and one methyl group, and it is primary. And this one, the carbon with only one electron is connected with three methyl groups. This is tertiary again. Kanna, is the order right? No, because
Not stable.
this is tertiary carbocation. Actually, this is the most stable one if you compare it with primary and secondary. So But in this option, it is given in the last position. So this is wrong. Now, can you please work on the rest of the option and could you please tell me the right stability order? If you want any help or if you want any clue, you just let me know.
How to find structure, ma'am?
Of second option.
Yes,
You're asking for second option.
yes, ma'am.
See, this is the carbon with only one electron, right, Kana? It is attached with only one R group, and rest of the things were hydrogen. So, what kind of free radical is this? Is it primary, secondary, or tertiary, or methyl?
Primary, ma'am.
Sorry, Mushkin.
Primary, ma'am.
Very good. It is primary. How about second one?
Secondary.
Very good, Kana. How about this one? I'll write the structure. This is the carbon with only one electron. The right side it is attached with CH2, CH3. Left side it is attached with two methyl groups. So this is one methyl group and this is another methyl group. What kind of free radical is this?
Tertiary, ma'am.
Yes, it is tertiary. How about this one? Carbon with odd electron is connected with three methyl groups. Notice three methyl groups, CH3.
Tertiary, ma'am.
Yes, tertiary again. If both the free radicals are tertiary, what we have to do? We have to check for number of alpha hydrogens, right? The free radical with more number of alpha hydrogen is more stable. How many of alpha hydrogens are there in this free radical?
9, ma'am.
This one.
11, ma'am.
This one. I'll mark you the alpha carbons. The carbon which are directly attached with this carbon atom with one electron, the alpha carbon. This is beta carbon.
8, ma'am.
Yes, this got just 8 alpha hydrogen. And this one?
9, ma'am.
9 alpha hydrogen. So which is more stable? The free radical with 9 alpha hydrogen, right?
Yes, ma'am.
So second option seems to be the right one because this is also tertiary, but this got 9 alpha hydrogen and this got 8 alpha hydrogen. And this is secondary, this is primary is least. So answer is second option. Okay. Shall we proceed?
Okay.
Okay. Please work on the second question first. Carbonium ion is also called as carbocation. They have given you the four carbocations, and we have to find which is the most stable one. First, we have to find whether it is primary, secondary, tertiary, or methyl.
B is tertiary, ma'am.
Yes, Kana, it is tertiary. How about first option? You are right, Mushkan. Second option is tertiary. Okay.
Ma'am,
How
C
about
and D secondary, ma'am.
sorry, Kana?
D one secondary, ma'am.
Very good. It is secondary.
First one methyl group, ma'am.
Very good.
C1 primary.
Very good, Kana. Now tell me which is most stable carbocation.
B, ma'am.
Brilliant. That's it. Now this first one. See, what kind of intermediate is that? They are free radicals, right, Kana?
Yes, ma'am.
So we have to find whether it is primary, secondary, tertiary, or allyl. As far as D is concerned, the odd electron or the carbon with only one electron is a double bond carbon. See, double bonded carbon cannot be an electron deficient carbon. It's highly unstable. Okay. Double bonded carbon cannot bear this odd electron, or double bonded carbon cannot bear a positive charge. It is highly unstable. Okay, so of course option D is unstable. Okay, okay. Now we'll check on the second option. This is an odd electron carbon, or the carbon with only one electron, and it is connected with only one R group. So it is
Primary.
primary. How about this one? Option C. Odd electron carbon is connected with sp2 hybridized carbon. This carbon is connected with sp2 hybridized carbon. So this is allyl. Okay. How about third option? Here also, this is the carbon with only one electron, and it is connected with sp2 hybridized carbon. So this is also allyl. Okay. We know that allyl carbocations are more stable than rest of the carbocations. That is tertiary, secondary, primary, and methyl. So of course, second one is not our answer. Between first and third one, we have to decide which is the most stable free radical. Both are allyl. How we can do? Could you please tell me which is primary, secondary, and tertiary? We know both are allyl. But in that allyl itself, we can tell the primary, secondary, and tertiary one.
Ma'am, this one, how find option that A and B, A and C allyl, ma'am?
See, allyl is nothing but odd electron carbon, that is carbon with one electron, should be connected with sp2 hybridized carbon. This is allyl. Okay, this is the condition. As far as third option is concerned, that is CH2, which is your free radical. It is connected with CH double bond CH2, right? So the hybridization of this carbon is sp2, right, Kana? So that is why it is allyl. Okay. As far as first option is concerned, this is our 6-membered ring. Top of the ring, we have one methyl group, and this carbon got one odd electron. And here we have one double bond, right, Kana? So this is the carbon with odd electron, and it is directly connected with this sp2 hybridized carbon, right, Mushkan? That is why it is called as allyl. First option is not only allyl, that also seems to be a tertiary one, because this is the carbon with odd electron. It is connected with 1, 2, 3. So 3 carbons. So this is tertiary also. So among A and C, A is most stable because that is tertiary and as well as allyl. Okay. Now we'll move on to next question. See, all the questions what we are discussing is from any entrance exams. Okay. So all the questions are very important. We are practicing, also we are strengthening the concepts. Okay, listen here. Here they are talking about the stability of a radical. So similarly, we have to arrange these radicals in terms of stability. It's very easy. If you want to try, please try, Kana. First, take one option, categorize them as primary, secondary, tertiary, benzyl, allyl, and all that. After which, check whether the order is right or wrong. If you want any clue or any support, please let me know. Okay, guys, listen. I'll work on this last option. I'll teach you how to understand this option. Listen here. This is the carbon with one electron, right? And that is attached with one hydrogen. And how many methyl groups we have? How many methyl groups we have? It is CH3 twice. So we have 2 methyl groups. 1, 2. So what kind of free radical is this? Is it primary, secondary, or tertiary?
Secondary.
Very good. This is secondary. Okay. Now we'll move on to this one. This is the carbon with one electron and it is connected with 3 methyl groups. 1, 2, 3.
Tertiary.
Very good, Kana. It is tertiary. Now, this is the carbon with one electron and it is connected with three C6H5 groups. We have to know what is that C6H5. Anna, what molecule is this or what compound is this? What is this? It is benzene, right? How many carbons and hydrogens we have? How many carbons and hydrogens we have in benzene? Yes, Mushkin?
6 carbon.
Very good, Kana. 6 carbons and
5 hydrogen.
okay. Actually, in benzene we have 6 carbons, and all the 6 carbons are connected with hydrogen atoms. This carbon with one hydrogen, this carbon with one hydrogen. So, how many hydrogen atoms do we have? 6 hydrogens. So, C6H6 is benzene. Okay, here we're going to remove one hydrogen, and instead of this hydrogen, we're going to substitute here. So this is nothing but C6H5. Okay, this is called benzyl or phenyl. Okay. See, this is the group they are talking about. So we have one benzene ring attached. So how many benzene rings they are talking about? It is C6H5 thrice, right, Kana?
Yes, ma'am.
So we have 3 benzene rings here. So this is tertiary. Not only tertiary, this seems to be benzyl also. Could you please tell me this one?
Secondary.
Yes, it is benzyl and secondary. We know benzyl carbocations are more stable, but number of benzene ring increases, stability also increases, right, Kana? Now tell me, is this order is the right one? This is the right one? Is this the order right?
No, ma'am.
No, because as far as benzyls are concerned, tertiary benzyl is more stable. So fourth option is not the right order. Now please check the rest of the options and come up with the right answer.
Ma'am, C option is second. First C option, second one is secondary plus benzene, ma'am.
Okay, which one, Kana?
C1, ma'am.
C1. What kind of intermediate is this?
Secondary plus benzene.
Very good. Secondary plus benzyl. Okay. Next is
Tertiary plus benzene.
very good. This is tertiary and benzyl. But what they are telling in this option is these are least stable than their normal tertiary and secondary. Is this right?
Mhm.
Is this right, Kana?
No.
No, because benzyls are most stable one, right? So third option is also ruled out. Next.
B1 tertiary, ma'am.
The first one is tertiary and benzyl as well, but that is also at the last, right?
Yes, ma'am.
So this is also the wrong option.
Option correct. Option A is correct.
Yes, option A is right. Because in option A, most stable is tertiary and benzyl. Next is secondary and benzyl. Next is tertiary, then secondary. Very good. Next. Now, they're asking us to arrange the stability of carbanion. See, I'll write the proper carbanions here. Carbanion P is nothing but CH3 minus. Q is C6H5 CH2 minus. R is negatively charged carbon. It is attached with hydrogen and it is attached with two methyl groups. Next is S. CH2 double bond CH single bond CH2, and this CH2 got one negative charge. So all these intermediates were carbanions, and we have to check for the stability order. We know the normal stability order, right? So first categorize these carbanions and come up with the right option. Are you guys working on it? Do you guys want any clue?
Yes, ma'am.
Okay. Kana, we'll see this P. What kind of carbanion is that? What kind of carbanion is that? This is negatively charged carbon. It is attached with 3 hydrogens. So what kind of carbanion is that? Methyl carbanion. How about Q? This is C6H5 and it is connected with negatively charged carbon. So C minus, so it is connected with one benzene ring and this got 2 hydrogens. So what kind of carbanion is this? This is benzyl carbanion and it is primary because this got only one benzene. And how about this one? This negatively charged carbon is attached with 2 R groups. So it is secondary. How about this S? Negatively charged carbon is attached with sp2 hybridized carbon. So this is allyl carbanion. Okay. And we know the stability order also for carbanion. What is the stability order? Benzyl carbanion is more stable, then allyl,
CH3.
Very good. Methyl.
Primary, secondary, tertiary.
That's it. Now, could you please come up with the right answer?
One second.
Mm. What is the answer? Bhumika, do you have any answer, Kana?
Ma'am, option B.
Option?
B, ma'am.
Okay. We'll check. Mushkan, what is your answer? We know that the most stable one is benzyl, right? Here, which is benzyl? Q is benzyl. So Q is the most stable one. So which means option C and option D were ruled out. Next, after benzyl, we know allyl is most stable. So next is it is yes. Next, this is methyl and this is secondary. Among methyl and secondary, the most stable one is methyl. So it is P. And least stable is your R. So the answer is second option. Very good, Bhumika. Your answer is right. Mushkan, you're getting my point.
Yes, ma'am.
Okay, right. Now we'll move on to next electronic effect, which is called mesomeric effect or resonance effect. Very easy. See, I have one benzene ring and we have double bonds inside the ring, right? And this ring is directly attached with an atom with lone pair of electron. Now, this atom is considered to be electron rich because this atom got one lone pair of electron, right, Kana? Now, what this atom will do is it will give its electron to the benzene ring because it is electron rich. So, this electron minimum that atom should have one pair of electron. So this got that one pair of electron, right? This pair of electron will get transferred between this carbon and this atom A. Now the problem is for this carbon atom because this got already four bonds, 1, 2, 3, and 4. Now this is going to be the fifth one, which is unstable. So the bond which is present inside the ring will get transferred to this carbon atom as negative charge. Now I'm going to write the next resonating structure. Why it is called as resonating structure? because I'm not changing the position of any atom. I'm just changing the position of the electron. Okay. So same six-membered ring, this bond and this bond will be undisturbed. Now already I have one bond between carbon and the atom A. Now I got new bond also, and this atom A gave its one electron. Now this now this atom doesn't have its lone pair of electrons, so this will have one positive charge. And one of the bonds was transferred to this carbon atom, right? So this carbon atom will have one negative charge. Okay. Whenever you're writing the resonating structures, you have to use this arrow mark. Okay, fine. Now what this negative charge will do is, this negative charge contains two electrons, right? This negative charge will get transferred between these two carbon atom as one bond. And this bond will get transferred to this carbon atom as negative charge. So what will be the next structure? Same six-membered ring. Same six-membered ring. This part is undisturbed. Here also I have one double bond, which is undisturbed one. Now this negative charge was transferred between these two carbon atom as one double bond, right? And this bond was transferred to this carbon atom as negative charge. That's it. This is the new structure. Then again, what will happen is, this negative charge is basically an electron, right? So this negative charge is getting transferred between these two carbon atoms, and this bond is getting transferred to the carbon atom at the top. So I have six-membered ring. This part is undisturbed. Here I have one double bond. Now I got new bond between these two carbon atom, and this bond was transferred to this carbon as negative charge. And finally, this negative charge will get transferred between these two carbon atom, and here one of the bonds will get transferred to atom A as lone pair of electron. So we'll end up with the first structure. So these are the resonating structure of this compound. Here, what we have to understand is, this is one aromatic compound, and whenever an atom is donating its electron to this ring, whenever an atom or a group of atom is donating its electron to the ring, then basically that is electron donating group. Technically it is called as plus M group, M for mesomeric effect. Or it is also called as plus R group, R for resonance effect. It is also called as, listen here, what is mean by electrophile? Electrophiles are electron loving species because they'll not have electron, right? So basically electrophiles are electron deficient one. Let us assume that an electrophile is approaching this compound. What electrophile will do? Electrophiles are electron rich. So they love electron. So where these electrophiles will go? The substrate got electrons at this position, and at this position, right? So at these three positions, electrons were accumulated. These sites are called as electron-rich sites. So whenever an incoming electrophile will approach only these three sites, could you please name the site? Whenever we have two substituences, or whenever I have one substituent at one carbon, rest of the positions can be assigned, right? See, this position is called ortho. This position is called meta, and this position is called para. Have to assign that. Listen here. I have one substitution here. Okay. If I have another substitution at the adjacent carbon, then these two positions are called ortho positions. Near to this ortho is meta. The carbon which is exactly opposite to the carbon which got substituent is para. Okay. So with reference to this A, these positions are called ortho, these positions are called meta, and this position is para. Now, where this negative charges are, where these electrons are accumulating at ortho and para positions, right, Kana? Here in ortho side, here also on ortho side, and here para side, right, Kana? Now, whenever the electrophiles are approaching this kind of compound, the incoming electrophile will move to ortho and para position. Definitely not to meta, because relatively meta is electron deficient. So this group is directing the incoming electrophile to ortho and para positions. So it is called as ortho para directing group, or it is activating the ortho and para position. So it is called activating group. That's it. I'll give you a few examples for ortho para directing group. Listen here. I have a benzene ring. To this conjugated double bond system, I have oxygen, and oxygen got 2 lone pair of electrons. If the atom which is attached to the ring got at least one pair of electron, then that is considered to be orthopara directing group. Oxygen got 2 lone pair of electrons, so definitely this group is orthopara directing. Here nitrogen is directly attached with benzene, and nitrogen got 1 lone pair. So this is also orthopara directing. And name of this compound is phenol. Name of this compound is aniline. I have benzene with oxygen, and that oxygen is attached with methyl, and this got 2 lone pair of electrons. So this is also called as orthopara directing, and this compound is called anisole. I have fluorine. How many lone pair of electrons this fluorine will have? How many lone pairs of electron this chlorine atom will have? On bromine, on iodine. See, all these fluorine, chlorine, bromine, iodine are from 17th group, right? So 17th group elements will have 7 valency electrons. So I'm going to distribute 7 valency electron around this fluorine. So how to do that? 1, 2, 3, 4, 5, 6, and 7. So this got only 1 bond pair which is attached with benzene. So rest of the electrons were lone pairs, right? So fluorine got 3 lone pair. Similarly, chlorine got 3 lone pairs. Bromine also got 3 lone pairs, and iodine got 3 lone pairs. So all these groups are called orthopara directing group, or plus M group, or plus R group, or activating groups. Okay. So next we're going to see the next